Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 8. Student, basically this is lecture 8. Inshallah I will show you the rest of the calculation. We did not complete that lecture. Okay, so 1.04 I am explaining that this is basically divided by 2 and plus basically once you got 19 point something from this value, and then that 19 point something will be further divided by the width of the panel. Okay, this width of the panel, transverse width of the panel, because this is the beam, so we have to consider one strip width. Okay, so that's why we are dividing that and that. If we're designing this beam, so then we have to use this transverse width. Like in the calculation you see here, we are considering the transverse or the supported slab width. Okay, so that's why you need to further divide this 39.44 divided by 2, further divided by that is 18 point, in that direction the width is 18.9375, and you will got 1.04. and remember, this is the only one, this panel. You have to count for this panel as well, and that is panel C. One thing is very important, that here I am using the maximum value, and the maximum value is for C, although 18.93 and 19 feet is close, so it doesn't make any great effect. Okay, the next one is the beam rev width, and this one is your slab above the above the beam. So your total weight is now 2.5.7 kg per feet. Okay, and ln is basically, remember we have two it should be remembered, we have two distinct panels. Remember, we have one exterior panel and we have one interior panel. Remember, this is very important, you must understand these panels. Clear? So if this is my beam, which I am designing, so this one is basically my exterior panel or end panel, and this one, the next one, that is C panel, is my interior panel. Remember, so that's why this is my end span and this is my middle span. Let me show you the graphical calculation of this kind of loading, how you can distribute the tributary area and so many things. Okay, so remember, let me show you here, let me rub it. Clear? That I will show you graphically that how you can calculate without those coefficients. How can you calculate by using the tributary area concept? Clear? You see that this is my beam, okay, and I have to calculate the distribution of load which is coming out from these panels. Remember, this is my region. Okay, this is my region. Okay, this is my region. Now here I have to distribute this panel into my tributary area, as panel B and panel C is square panel, so that's why I got this kind of calculation, graphical distribution, that is square. Okay, tributary area, and this is the triangle area load which is transferred to this beam, and this is the area which is transferred to this beam. This triangle will distribute load to this beam, and similarly this triangle will distribute to this wall, and this triangle will distribute load to this wall. So let me show you the rest of the calculation. Okay, here I have this one. You see the distribution, the total area which is supported by this beam B1, and you see all the beams. Now I am calculating loads for this portion of the beam, so I divide the panel B into tributary area. Okay, the height of this panel, or you can say the half width of this panel, is nothing, it is just only this span divided by 2, 9.46. now this is my triangle, 9.46, and this is as there is 19, so 19 divided by 2, which is close to 9.46. okay, so After dividing the whole area into tributary area, what you have to do, you have to find out the area of this shaded triangle, one triangle, okay, which is similar to all other triangles, okay. If there is any differences, then you have to find out, okay, for each triangle area. So as the panels are similar, symmetrical, so that's why I just only calculate the area of this one triangle. So here you see I choose this beam, okay, and I just show these triangles, this one, remember this one is similar to this one, but this one is changed, a little bit change. You see A1 triangle number 1, 2, 3, A1, A2, A1. Again, the height of this triangle is 19 divided by 2, which is close to 9.46, okay, not greater difference. The span of each triangle you see. Now the area of triangle 1, this is half, okay, this is basically the formula which is used for calculating the area of a right angle triangle. So 1 over 2, 9.46 is that one, and 18.937 is for half, okay, and multiplied by 2 because we have two triangles. So that's why this is the area of A1, okay. Still I don't divide it by 2, okay, remember. And a 2 triangle is same, okay, this is 180 and 179 close, so this is one. Now WU, which is the load distributed, which is the WU load, we already calculated in lecture number 2, so that is the slab weight. Now if you are interested that how much load will be applied by this triangle, so you need to multiply that load with the area of that triangle. So you see, you got P, that is point concentrated load, A1 times WU. You calculated A1, that is 39.14, and divided by 2, okay, you have to multiply them with the WU, okay. So you got 39.14, as your area is 179, so that's why still that is not divided by 2. If you divide it by 2, so I think so you got 19 point something, okay. And similarly here, A2 area times this W, you got P2, clear. So you see 39.44, 39.14, they are close, so therefore we will just using this major case. Here you see loads only from one side, still we are not counted for the other side. So converting to UDL, now point load is converted to UDL. How? You see, if you calculated these P values, so you select the maximum value of P, and then you have to use L minimum. You see the spans 19, 18, so you need to use the L minimum. This is the formula, okay. Dividing, you got 1.04. I already explained that. I will show you graphically that from where this 1.04 comes out. So keep per feet. This is from one side. If you want to add the other point, the other side effect, you just need to multiply it with 2. So you see, when I multiply it with 2, 1.04 times 2 for double side, I got this one. Adding beam, rib and slab weight, you already understand this. So adding that, 2.517. This is my final UDL loading. Now I have to use my coefficients, okay. These coefficients I explained in lecture number 7, and these are my shear coefficients, and you know I explain these shear coefficients as well. If this is R1, ACI code basically give me these coefficients, WU and divided by 2. Remember, this is my first interior support. At first interior support, at the exterior face, you have the same shear, but that is 15% more than this one, and the rest of the shear will be same. And again the case will be repeated for the first interior support for the exterior face, and 15%. Only these two shears are different, the other all shears values are same, remember. Then next I draw the movement diagram. You see, this is my positive, so my positive. This is 110 my negative, so 110 my negative. The other coefficient is 111, so that start from here. and 116 is positive, 116 is positive, and this is the way. And I already explained this diagram in my lectures, which is right on my YouTube channel. You can watch. Okay, here you can understand the whole this kind of diagram. Then shear diagram, so I will jump to R1, then I will, due to that loading, basically I have to go down, okay, here, and due to that reaction I will jump, and then due to load I will then again jump, and then due to load I will down. Okay, now the very important thing is that we need to find out this distance where the shear becomes 0. So I assume that it is it's an x. The next distance is L1 minus x. Using the similar triangular rule, x divided by that ordinate, that is 23.83. Okay, WU is determined. We know about ln1, so divided by 2, you got this one. Okay, and using similar triangular rule, okay, simplify this equation, you got x is equal to 8.80. So this x is basically from the face of the support is basically 8.804. Clear? And that distance will be 10.13. So this is very important. Okay, this is very important and it will help you. If you are passing a rectangular panel, so in a rectangular panel, the tributary area is trapezoidal, remember. And this is LA divided by 2. You have to remember this angle is 45 degree. Okay, so if you are interested to find out this distance, you have to use, remember, this triangle. This angle will also be 45 degree. So you find out this h. Okay, from this similar triangle rule, you have this base and you have this angle. You can find out from sine rules. Okay, trigonometry, you find this h, and h will be here, and similarly this h will be here. So you have this total length. So subtract these two HA. Okay, you got this one. Okay, and then as you determine the WU, so you multiply that WU with this distance. Remember this interior distance. You got the load intensity in kip per feet. Okay, and then you have trapezoidal loading. Okay, and if you are interested to find out P1, P2, then you for P1 you use this triangle and this one, and the rest of the thing. Remember, if you are interested to learn this tributary concept, you have to go to the structure analysis book of Hebler at edition, and that is chapter 2, I think so. In chapter 2, basically here you see so many examples on it. So please visit that structure analysis book of R.C. Hebler at edition, and chapter 2 you understand how these tributary area will be used and to calculate the loading. Okay, now going back, you understand the load distribution, how load comes out. Okay, and then again you see for ends panel we will use now we will start design. Clear? We will start design. So design is simple. If you know about your moment coefficients like this one 11, so now we are designing end span. Remember, we are designing end span. So this one, remember, we are designing this end span. Okay, this one. Now if you are designing that end span, this one, remember, we are designing now this span. This is my end and this is my interior. Okay, so I am designing for this middle movement, so that why M positive 111 WU ln square into 12 to convert into inches. 111 I got 2.5 already explained, ln is explained, and 12 you got 984 kip inch. If you are providing 3 number 6 bar, this is from experience, remember. Okay, 3 number 6 bar, it will cover this movement. How? Because you know the formula. I already write down this formula. MD is equal to 0.9 I think so, where it is D minus A is Fy, okay, divided by 1.7 times I think so FC prime something. Here I think so A is Fy. Let me check this formula. Okay, I think so I write down here this formula, and you must remember. Okay, this formula is a very important formula which directly give you this one. Okay, here you see 0.9 ASFY D minus ASFY 1.FC prime into P. Okay, the same formula. So this is important, very important formula. Okay, it will basically lesser down your calculation work. Okay, so here you see FC prime into B. Clear? So AS is now, if you are providing number 6 bar, so your AS will be 3 times number 6 bar area 0.441. So you got the AS, just plug the value of AS, you know all the values. D is 15 inches and you got the moment capacity, and that moment capacity will be greater than this 9 and 4. Remember, that moment capacity will be greater than 9 at 4. Clear? So therefore they are directly used 3 number 6 bar. I will explain. Okay, M negative 110 WUL, and this is 1083, and to cover this movement you have to use 4 number 6 bar. So here you calculate AS and again plug the value here, you got the moment capacity, and that moment capacity will be greater than this one. For metal span, this span, okay, I have coefficient 116, you already know this. This is 677, so 2 number 6 bar will cover. And for negative movement 111 basically, so for 111 I have to use this one. So basically then we will use positive and negative 111, but remember this is 111 is basically for the middle span. Right now this one, clear? This one. So we did calculation for this one, for this one, and this one. Remember very important information that sometime code says that you have to, because these 110 111 coefficients are for negative reinforcement, okay, for negative moment. So sometime we take average, or for conservative approach you can select the larger coefficient, that is 110. Clear? And for this movement basically we will use 3 number 6 bar. Clear? Now we are designed for these movements, how these 2 number 6 3 number 6 comes out. Okay, so AS minimum is 0. Our rho minimum is already we know 0.0033 BD, B is 12 and D is 15, so we got minimum steel area is 0.5. remember, to cover this movement we need 2 number 6 bar. Clear? We need 2 number 6 bar, so our bar should not be less than 2 number 6 bar. Clear? So this is moment distribution, and here we have here AS max, so 0.021, this is my rho max. Clear? So rho max times BD, we got this is the maximum steel reinforcement. So this means that AS provided should be greater than AS minimum. Okay, should be greater than AS minimum and should be less than AS max. This is the ductility check. Clear? We have to ensure this ductility. Now effective width of beam, because as you know this is a continuous slab system, so that's why we have to check T-beam or rectangular beam analysis. So calculating B effective L by 4, BW 16, HF 100, and center to center distance, that is 227.25. Remember, I have completely explained a T-beam analysis right here in this playlist. PRC 1 plus 2 courses, PRC 1, 2, here I completely explain the analysis and design of T-beam. Clear? So if you visit this playlist, you can see and you can watch the design of as well as plus with theoretical cutoff point, actual cutoff point. Okay, so in very detail in this playlist. So here we have to select the lower value, that is BF 56.8 inch. Now for rectangular analysis, remember whenever we have positive movement, for positive movement basically we check whether the beam is a T-beam analysis or whether it is a rectangular beam analysis is needed. Remember, if you have a continuous beam system, let me show you. if you have a continuous beam system, so as let's say here your support, here your support, clear? So you just check the positive movement region, and in negative movement region the beam behave like an inverted T-beam. So there the beam is already a T-beam, but here you have to check rectangular beam analysis or T-beam analysis. So BW is known, BF is known. Assuming that A is equal to HF, you already know the calculation of T-beam analysis. We assume, okay, the movement is the positive movement. Remember, here I am checking for positive movement. So 9 at 4 inch kip and my D is 15 inch. Using the same formula, you got your A is, that is 1.32. So you just need to plug the value, you got this one, and for this movement you need 3 number 6 bar. For this steel you need 3 number 6 bar. Now revise the thing, recalculate A, whether it is a T-beam or not. So how you can calculate A is Fy times 0.85 FC prime, okay, into B EF. If it less than HF, so this means this is a rectangular T-beam and we need T-beam analysis. Oh, sorry, a rectangular beam. This is an rectangular beam and we need a rectangular beam analysis. Okay, so please check these calculations. Okay, how we can check a T-beam and rectangular beam analysis. Okay, remember one thing that you design. Okay, so one thing that you have to check the T-beam or rectangular beam analysis for positive moment, not for negative moment. Then for negative moment it is also working as an inverted T-beam. Okay, so the moment is 1083, that is the maximum moment, and just plug this moment here, okay, here, and you do the calculation, you got the answer. A is equal to 1.36 inch square. Okay, and for this steel area you need 4 number 6 bars. AS will be, if you provide 4 number 6 bar, your AS provided will be 1.77, remember. And for positive, that is for middles, for the middle span, the positive moment is this one. So you need to check the T-beam or rectangular beam analysis and then just plug this value M positive here, you got AS is this one. And if you provide 4 number 6 bar, your AS provided with 0.88. Okay, so this is the calculation, how you can lesser down your calculation work, okay, in exam, as well as this is we do this calculation in practical field, basically in design. This is the way how we can lessen down our calculation work. Okay, if you are go towards head and trial rule, that is very lengthy and very time consuming method. So this is the most easiest approach to design a beam. Now what I have to share the detailing of this beam. Okay, so the detailing of this beam, let me show you. I have this one, clear? So you see my wall support, and you see that these are, now I am not dealing with shear reinforcement. In later when I design this for shear reinforcement. Okay, I will explain this one. Remember, this is the detailing. Okay, you see these are my bottom bars, this is my exterior panel, this is my interior panel, and this is my exterior panel. Okay, so here my positive movement and here my negative movement, this is region, and again positive movement 1 over 16, 1 over 11, 110, 111. Okay, now you see in the for positive movement we provide 3 number 6 bar, and for negative 4 number, that is 1083 kip inch, 4 number 6 bar, and again 116, that is I think so 677 kip inch movement, so 2 number 6 bar. You see that 2 bars, basically 2 number 6 bar as supporting bar, that is minimum reinforcement. Okay, supporting bar, and here you have 4 number 6 bar, and here again you have 4 number 6 bar. You see the lap zones, but lap you have to provide it will be alternating lap. Remember, I will share also the left lengths, that is whether it will be a 50D or 45D. Inshallah, I will share that table of ACI. You see the span width, okay, and okay, you see the hook, that is 12 dB, and okay, this one. Now this is very important. This is the plan view, top view of the beam. You see 12-inch width of the beam, and the full line, basically you can say the darker line is your continuous line, is basically your bottom bar, and the dotted bars are your top bars. Clear? Now you see we have basically these two continuous dotted lines are the supporting top bar. Clear? And here you see this 3 number 6 bar. So one bar is cut here, okay, at a distance of how much? L by 8. You can cut this bar from the face of the support at a distance of L by 8. Clear? And similarly here, okay, but here we need 2 number 6 bars, so that's why you see 2 number 6 bar. You see the lapping, okay, this is interesting, important. One bar is basically lap here, the other bar is a lap here, okay. So this is the way how we can alternating the bars. The dotted, this line are extra bar which is provided for the negative moment here, and the length, this length is L by 3 and L by 3, remember. And yes, their movement is basically 0, so therefore I do not provide basically extra bars here. Just 2 top bars will be here, that dotted lines, that is supporting bars, and it will work like a for that amount of negative moment. But although this is simply supported, so that's why I don't use it. And this winds up basically the detailing of this beam. Basically, if you have any question, you can ask, okay, in comment box. Now what we have, basically we finish. And remember, for cutting up bars you can use this chart, you can use these formulas. Remember, this one L by 3, this one L by 8. So the bar which you are cutting down is a distance of L by 8, remember, L2 by 8. So you can use this one, this chart, for cutting up bars. The first one is L by 4, but we are not providing that. We are just continuously provide 2 bars as a supporting bar. Clear? So next is the shear design. Clear? Next is the shear design, and inshallah in next lecture I will do that design. Okay, shear design, as well as I will design basically the B2 beam as well. So this winds up. Okay, if you have any question, any suggestions, please share your suggestions and your questions. Thank you for watching.